reach out to me primarily because we are doing what is called quantum key distribution, right? Now, this particular talk or lecture has a certain flavor to it. It's fiber optic. So, just to set the tone, we understand that we have both free space and fiber optic quantum key distribution. So, this is free space and this is fiber. And the lecture today is primarily, my lecture today is about fiber optic, and I believe one of my colleagues from IIT Delhi will talk about the free space version of quantum key distribution. Now, to understand fiber optic quantum key distribution, which we'll call as FOQKD, we need to first understand fiber optics. Right? And so I will start there with a very simple diagram of how light propagates down a fiber. So a fiber is primarily glass, and so this has glass, this is also glass, and this is also glass. And what is on the outside, if you look at the diagram, it's a circle, it's a cylinder. So this is your fiber. In the middle, we have what is called the core, and outside we have what is called the cladding. The only real difference between the core and the cladding is the refractive index. The refractive index of this, which we'll call N core, and this is N clad, N core is greater than N clad. What that allows you to do then is something that we learned in high school, which is called total internal reflection. So this is N2, this is N1, and you can go with a ray of light up to a certain angle, and then it will reflect back in what is called total internal reflection. Okay. Now, most of us should remember. If not, I can just spell it out. That total internal reflection, or TIR, happens when we are unable to satisfy what is called Snell's law. So this angle will be, or rather let's call it, this angle will be theta incident or theta 1, and this angle is called theta transmitted or theta 2, and theta t is equal to 90 degrees. So this equation just becomes n1 sine theta I is equal to n2. So I can calculate what is called a critical angle. Theta c is equal to sine inverse of n2 by n1. Now remember, n2 was less than n1. So n2 by n1 is less than 1. And you can take the sine inverse of n2 by n. In school, we basically said that, okay, we will do this with, I remember doing the problem where n1 was 1.33 and n2 was air because we were a swimmer in the swimming pool. And so we could calculate this. However, in this particular fiber optics, N1 and N2 are close to, both of them are close to 1.5, which is the refractive index of glass. So one of them might be 1.49, the other one might be 1.51. They're both approximately 1.5. So what we are aiming to do in a fiber is basically launch light. So now this is my fiber, this is just the core. I'll say the cladding is up here. This is all the core. And what I'm aiming to do is launch light such that it goes here, bounces back, goes here, bounces back, and so on. And this allows me to pretend that it's effectively going forward in this direction down the fiber. So that's one of the basic ideas. And the fiber we talk about is, we call it a single mode fiber, or SMF. More specifically, we talk about SMF 28. Now, this picture that I've drawn out here is the ray picture. It's not the mode picture, right? So this is, the word is mode. So what I've drawn out here is the ray picture, it's not the mode picture. So what exactly do I mean by the mode then? If I look at this fiber again, if I look at the cladding out here, sorry, the core out here, and the cladding, let's say somewhere out here, single mode means that all the light is traveling primarily in the core of the fiber. Maybe some of it is leaking out into the cladding. Specifically, if I were to draw as a function of the radius, right, if I were to draw what this intensity would look like, it would look something like this, or not the intensity, but the electric field. Look something like this. So most of it is sitting inside the core of the fiber, which is, let us say, A, right? So this distance is A, and most of the electric field is sitting inside that fiber. It is important to understand that some of it is leaking out. Right? That is because the mode is defined as, not by, as the distribution of the electric field represented by the letter E. It's usually a vector, so you put a vector sign, that propagates through the structure without any change. That's what we mean by the mode, right? Propagates through the structure. So in this case, it's propagating down along the direction Z through the structure without any change. It will still continue to look like what I've drawn out here. It will have this, most of the electric field will be within this region out here, and it can be plotted along the radius, and it will look something like this, and it will continue to propagate forward along the Z direction, right? Okay. Now, hopefully we understand what a mode is. Now, since I've introduced the word single, I have to actually now explain to you why we call it single mode. And that's because if I were to look at the core and the cladding again, where this was my A, and I were to plot the electric field again, I might see something that looks like this, which would mean that I have some electric field sitting here and here as two lobes. Okay. Now this quantity is the next higher order mode. I'll call it E2 and I'll just call this E1. Let's call this E2. That's not the right nomenclature, but for purposes of our conversation, that is fine. This is R, and again you have A sitting somewhere here, right? But the maxima is further inside. This particular distribution could also have been drawn with modes out here and out here. Just like I drew it, two vertically things, I could have drawn it like this. Turns out that both of these are what we call degenerate. All right. The word degenerate is also something that we need to think about a little bit. Degenerate means having the same energy. Now that I've introduced the concept of energy, I have to define it. So we can claim that the energy is proportional to E square. All right. So it doesn't matter whether I have these modes as vertical or I have them as horizontal. They have the same energy because I could have just rotated the optical fiber and I would see this. There's nothing very typical about this. Even in a fiber, you could have some things like this even in free space, right? But understanding the fact that there are modes and that we are working primarily with what is called single mode fiber is important. Uh, does it mean that a single mode fiber will never have these higher order modes? The answer is yes. However, remember the mode is defined as a distribution of the electric field that propagates through the structure without any change. Now, you and I have all seen practical fibers, deployments of optical fibers, and this is the fibers are typically bent, and that implies that I could lose energy from E1 to E2, right? So this would constitute for one type of loss, or what I would also call crosstalk. Okay. So this is sort of a lot of very basic understanding of fiber optics, right? You have a piece of glass. Let's see, you have a piece of glass. In the middle, there is a piece of glass with a higher refractive index that I call the core. And outside is a piece of glass that the slightly lower refractive index that I call a cladding. And it has been tailored such that it will largely have only one type of distribution or mode that I call a single mode fiber, where the electric field is mostly in the core of the fiber. If you bend this fiber, then what happens is that you violate this notion of critical angle at total internal reflection at the interface. So if I bend this like this, then the ray that's coming might escape because it's no longer looking at the flat critical angle. So it's no longer seeing the flatness out here. Instead, it might just escape because I bent it. So bending causes loss. And that's one type of loss. Another type of loss that we have is scattering. Why do I have scattering loss? Well, it's glass, it's amorphous, and it has impurities. Right? So, not all the light that I send in comes out. If I want to look at this, I usually plot it as a function of wavelength. And when I plot it as a function of wavelength, what I will see is that it decreases with wavelength and then it reaches a minima. And beyond that, you again have an increase. All right. So I'm trying to see if I can very quickly find a plot for you that shows this. Yeah. So it will look something like this. Maybe. And this first part of it is sort of around, I would call 1300 nanometers. And the second part of it is 50 nanometers. This value out here is about 0.2 decibels per kilometer. This value out here is about 0.3 decibels per kilometer. You could also look at it a little somewhere else, and we call that at 800 nanometers. So we have 800 nanometers, which is our first window. We have 1310 nanometers, which is our second window. And we have 1550 nanometers, which is our third window. On the y-axis out here is what we call attenuation. Its units are decibels per kilometer. Okay. Now, this is an important thing for us to understand because you will hear when people talk of quantum communications, you will hear them talk of different phenomena, but not all of them are actually focused at 1550 nanometers. So anytime someone's talking to you about um, communications on fiber optics, you should ask yourself, are they talking 1550 nanometers or are they talking 1310 nanometers? Right? It's a big difference because this looks like a small difference, zero point 0.3 and zero point 0.2. Let me give you an example. If I do 100 kilometers at 1310 nanometers, that becomes 0.3 into 100, that is 30 decibels. On the other hand, if I do 100 kilometers at 1550 nanometers, that becomes 0.2 into 100, which is 20 decibels. Now, for those of you who don't remember, power in decibels, dBm, is defined as 10 log 10 power in milliwatts divided by 1 milliwatt. Okay. So, a loss, so if I have a ratio, let us say uh, P0 equal to 1 milliwatt, this implies that P0 is equal to 0 dBm. Similarly, if I say P1 is equal to 10 microwatt, this implies that P1, which is 10 log 10 of 10 microwatt divided by 1 milliwatt, is equal to 10 log to the base 10 of 10 to the power minus 2, which is minus 20 dBm. Right. So the difference between going from here to here, which is a factor of 100, right? I've divided, so P1, P0 by P1 is actually 100, is 20 dB. A factor of 1000, so this is a factor of 100. This is a factor of 1000. So people often don't appreciate it, that a small change of going from 1310 nanometers to 1550 nanometers, right? Just doing this, I'm doing 1310 nanometers instead of 1550 nanometers, means that I end up losing 1000 times more power instead of 100 times more power over the same distance of 100 kilometers. That is a problem, right? So it turns out that if I send down this fiber, so here's my fiber, and now I'm going to draw it like this. This is the symbol for an optical fiber. If I send P0 down here, and this is 100 kilometers, what I'll get out here is P1. If I'm sending it at 1550 nanometers. On the other hand, if I send P0 down the same 100 kilometers at 1310 nanometers, I will get P2, which is 1000 times smaller. So I sent, here I'll get P1 by P0 equal to 0.01. Here I get P2 by P0 equal to 0.001, right? A factor of 10 smaller. So please remember that, right? Anytime someone's talking to you about these things, you should remember that we have a certain reason why we choose 1310 nanometers So this 1310 nanometers is very critical for us compared to any other wavelength. It is the minimum of this curve of attenuation versus wavelength in a glass fiber, in a typical glass fiber that we are all commercially using. The other very basic concept that I introduced was that of energy. Okay, and I sort of said E is proportional to electric field square. We'll do a little bit better than that now. I'm going to now go ahead and say that I can calculate E as the number of photons times Planck's constant multiplied by the speed of light divided by the wavelength. And this energy depends on these quantities, and there's a wavelength also in the denominator. So if I can send if I transmit n equal to 1 photon down this optical fiber. So if I transmit n equal to 1 photon at 1550 nanometers, then at 1550 nanometers down L equal to 100 kilometers, then I will receive the photon with a probability of 0.01. Same number that I have out here, right? That is now called a probability. It's now called a probability. It's no longer transmit and receive power. It's a transmit is probability 1, receive is a probability 0.01. And of course, if I do it at 1310, if I do this at 1310, if I send n equal to 1 photon transmit at 1310 nanometers down the L equal to 100 kilometers, then I receive with probability of 0.001. What does it mean to say that I receive it with the probability of 0.01? I can't send one photon. I have to repeat the experiment hundreds of times, right? So I will send one photon maybe 1,000 times and I will receive it 10 times. Because I can do that, I can estimate what this probability is as 0.01. So I have to repeat the experiment. Must repeat the experiment hundreds of times to get these numbers. Okay. If I want to do the other experiment, I have to repeat it thousands of times. And that's how you understand probability. Again, I emphasize this because people don't sometimes always pay attention to it, and we end up with the wrong conclusions when we are talking about probabilities. Simply because we are saying that if the probability is 0.001, you need to run the experiment few thousand times. If you run it a few hundred times, you cannot get that 0.001 number. Similarly, for the case of 1550 nanometers, if I want to receive that photon, I want to receive the photon and say that it is coming with a probability of 0.01, I have to repeat the experiment hundreds of times. Okay. So this is one aspect of fiber optic communications that you need. The second aspect that I will talk about. Let me stop the video here. Okay. The second aspect that I will talk about. Give me a second. Let me change my paper style. Okay. Let's take a look again at this particular picture and let me copy it out. No, I can't copy it very easily. Never mind, I will draw it again. Let's take a look at that picture again. This time I'll draw it a little larger. Attenuation in decibels per kilometer, and this is wavelength. And it looks something like this. Uh, Maybe I didn't draw it very well. Let's try it. And you should remember that this side was 1310 and this is 1550. Now it turns out that we're talking of about 150 nanometers out here. This separation is about 150 nanometers. So from the scale of this graph, you should be able to see that there is a region out here that is low loss. Incidentally, I forgot to mention this little peak out here is called the water peak. And that's because the glass has some water content and water will absorb light at this wavelength around 1400 nanometers. Right? So a lot of the free space optics works at 800 nanometers. That is why I was writing that down. This is usually where free space optics works, and you'll hear more about it from Professor Bhaskar. A lot of the fiber optics is used to be done at 1310 nanometers, but now it is done at 1550 nanometers, and that's because we have a window out here. This is, oops. So this is called the C plus L bands. Okay. The C plus L bands allow us to, by defining the C plus L bands, we are saying that they're bands, they have many wavelengths. And actually, what they are as many as 40 wavelengths, all sitting down here. Okay. They're called bands and wavelengths on the ITU grid. ITU stands for International Telecommunication Union, and it defines the particular wavelengths that we can use to transmit on an optical fiber. So most of us would remember that if you had an experiment where you sent white light, it split up into different colors, starting from violet at the bottom to red at the top. Right? That was the way we were taught the colors of the rainbow. Just so I complete this a little bit, let us say this is lambda b and this is lambda r. We have lambda b less than lambda r, which means that shorter wavelengths have a lower, sorry, shorter wavelengths have a higher refractive index. Okay. That's just a note for the future. Okay. But what is important is that each of these colors actually works independently, and there are many colors. So the colors don't talk to each other. I'm going to say talk. Okay. What do we mean by talk? That means if I take a, let's say, a red laser and I take a green laser, should probably use different colors. And take a green laser, I will get a green spot out here and I will get a red spot out here. They don't talk to each other, they don't interact. In this central region, nothing happens. Right? I can go further and say I will take a red laser and I will take a green laser and put it on top of the red laser. And what I will see is a red spot on top of, and on top of that is a green spot. They don't talk to each other. If I were to put my prism out there and allow this to fall, then I would get red spot on top and green spot below. But if I don't do that, and I just look at what is happening when they co-propagate, they don't talk to each other, which is advantageous for us because we can then use this region, right? And we can use it for different types of things. Commercially, what people will do is they will say, okay, I will use one of these and send data from Chennai to Bangalore. Somebody else may use another one of these and send data from Chennai to Hyderabad. Right? And so they break up the routes in our optical communication through these different channels. Why is that good for us? Well, if I want to build a quantum communication network, which I don't know why I'm putting arrows on it. Sorry. If I want to have a whole band of these and I have individual wavelengths, I can choose one of these as the quantum and I can choose one of this as the classical. So this could be lambda 1 and this could be lambda 2. And the two can co-propagate on the same optical fiber. Assuming negligible crosstalk. Okay. So now I've introduced the concept of wavelength division multiplexing. All right. Okay. I am now looking at the new concepts that I have introduced. I've introduced loss, attenuation. I have introduced wavelength division multiplexing, WDM. And I've also introduced this idea of a quantum versus classical. I had introduced it earlier. I had actually introduced it Up here, where I said E is equal to nhc by lambda, this concept is a concept of quantum optics, right? It says that I have one quanta of light at wavelength 1550 nanometers, and I'm calculating its energy as hc by lambda. If I have more such photons, then I will get a total energy of nhc by lambda. On the other hand, when I write this equation, it's classical. I'm saying E is proportional to the magnitude of electric field square. So this idea of being able to do both of them is the wave particle duality of quantum mechanics, right? Related to a photon. A photon is both a particle and a wave. So I have this proportionality to E square up here. Oops, where did it go? I have this proportionality to E square happening here, and this is a classical idea. And similarly out here, I have E is equal to nhc by lambda, which is saying that this is, if I have n photons, this is the energy of. Okay. So I am going to now start moving slowly into describing what is happening with a photon, right? But before I do that, there is one more concept, which is the idea of polarization. And that's simply because when we think of an electric field in time, we say that it is oscillating in time. So at any given location, it's oscillating in time. And this is at some given location Z. On the other hand, if I say, how does it look like in space? It is oscillating in space also. So this is why I write it as E of t. Now, this is an incomplete description, because you actually need a third quantity, and this third quantity is the polarization, and we put this vector notation on top of that to determine polarization. So if you think of an electric field, it's basically written as the amplitude times a sine wave omega t minus kz times a vector. In this case, let me say x. Right. This is one way of writing what is called a plane wave. Another way of writing it is again this vector E0 e to the power j omega t minus kz, but I have to have the polarization. So the polarization is an integral property of electric fields. And if you start thinking of it from the quantum picture, you can still argue that polarization should be there for every single photon. Okay. Now that I have polarization as every single photon, so it's easy to remember. I now have these three quantities. I have the amplitude, E0. I have the polarization along x. I have the frequency, which is 2 pi f, which is omega, right? Or rather, I should change that and say I have the radial frequency, omega as 2 pi f. I have the wave number 2 pi by lambda. These two are related. Why? Because F lambda is equal to C. Or in glass, it is C divided by N, where N is my refractive index. Right. So I have these descriptors already. And when I start doing quantum key distribution, polarization is one of them that I can work with. The other one that I can work with is this quantity out here, which is called phase. Right. And just so you understand phase, this is phase equal to 0. This is pi by 2. This is pi. This is 3 pi by 2. And this is 2 pi. Right. Now you'll notice I didn't start off at phase equal to 0 out here. So here phase is greater than 0. Right. And why did I do that? Because my definition of time and my definition of z is arbitrary. Right. So if you want a complete description, I could actually write it as E0 e to the power j omega t minus kz plus phi naught times x. But this is some arbitrary phase relative to my laboratory. But remember, there are many things that are critical out here. There is time, there is z. Z, I can again say my laboratory is z equal to 0. Right? So one has to remember this picture a little bit when we start doing quantum communications. Okay, I've spent about an hour writing on my pad so that I could introduce some of these concepts before I throw you into the world of quantum communications. Can I take some questions before I move forward?
Yes, sir. There are few questions
Yeah.
on the chat window. So
So
somebody asked an hour ago, what is window? What is window? Please explain.
window, and forget where I use the word window. Somebody has to remind me where I said window.
Okay, so we can probably move to the next question. We probably will get some clarification from the participant. So,
Okay.
what is polarization in simple terms? So we have
So,
actually covered introductory 5 lectures on polarization optics
so
before
they
we
should
came.
know it, right? They should know it.
They should be knowing it, but then if you want to
Okay.
explain it.
Uh, the easiest way to explain it is with is an example that I do not know if you can see it. Let me see if I can show it to you. I do not know how well this is visible, but you'll see the color changes in the middle when I have all these glass slides stacked. And then I can make it darker by rotating one of the glass slides. I do not know if that's visible to you very much. Let me try with two. There are two glass slides here, and in the center, it is darker where the two are orthogonal to each other. If I rotate it such that they're parallel to each other, then it's not supposed to be as dark. But I think you're having it a little hard for you to see it on the thing. So a polarizer is like a fine mesh. Okay. A polarizer is like a fine mesh. Think of a fine mesh like this. In which case, if the light is propagating through the mesh, only the electric field that is vertically polarized will go through the mesh. And so that is polarization. It is basically saying that any disturbance only along a particular direction goes through. And so we've come up with the notion of polarization to explain this phenomena where it gets darker in one direction, and if I rotate the polarizer and make it horizontal, then electric field that is only horizontal will go through. So you have to ask what is oscillating out here, and it is this electric field that's oscillating up and down, right? So that electric field is what we are describing along the x direction and saying that that is the polarization. I don't know if that helped, but that's the best I can do right
Regarding window, there is clarification which says three windows. I don't know what does he
now.
mean.
Right. Okay. I see. This is, I was referring to this chart out here. We call them the windows of optical communication because there are three wavelengths. There was this 800 nanometer range. There is this range of wavelengths around 1300 nanometers. So we call them window. And here there is this range of wavelengths around 1550 nanometers. So these wavelengths are identical. They are unique, 800 nanometers, but there's actually a range around it. That range is what we're calling a window.
Okay, so that's that. I mean, that's the questions which have been posted. If you want, we can take 5 to 10 minutes break.
Okay. No, I think I'm okay to go on if people want to go
Okay,
on, or maybe in 5 minutes I'll go get some water and come back.
yeah, we can
Okay.
take 5 minutes break.
Yeah. Okay.
Professor Prabhakar, can we continue?
All right, we can continue. Uh, Let me switch to from my iPad to actually sharing something else. Then we can move a little faster also. So I have to stop sharing. I will share instead. Uh, Home tab. All right. So I'm assuming you can now see
Yes, we
the
can see
picture I
the.
was drawing, right? What I was calling the windows. This is the attenuation optical fibers. You have the first window, the second window, and the third window. And this is the math that I had done for you. 100 kilometers in the third window means 1 in 100 photons will reach. I also introduced these concepts to you. This is a picture that says what is polarization. This is the idea of color. This is the idea of phase. So now, when we start putting those things together, this is what we call the ITU grid. And you'll notice that there is the O band, the original band, there is the short band, and there is the convention band and the long band. So this region of 1500 that we are talking about, 1550, has actually got these 40 channels, all spaced close together in what is called dense wavelength division multiplexing. In the O band, they had broader spacing, and that was the original band. The reason that we stick to 1550 for classical communication is because we have amplifiers in classical communication. Right? And why do I need to use that? I need to use that because classical communication is limited to the 100 kilometers. And after 100 kilometers, I put what is known as an erbium doped fiber amplifier. And this erbium doped fiber amplifier then amplifies the signal and goes to the other end. So I can send information on different wavelengths in this ITU grid, amplify it every 100 kilometers, and receive it. If I want to do both classical and quantum on some of these lines, I have to make sure that the classical does not leak into the quantum. And the way to do that is to isolate them. Typically, these are isolated at the 50 dB level. So I explained to you how decibels, every 10 decibels is a factor of 10. So 50 dB is now 100,000 times. And we need another 30 dB to isolate classical and quantum. So that I need 100,000 into 1000, that is 10 million times into 1000. 100,000 into 1000 is 100 million times isolation. What does it mean? It means that if I send 100 million photons on the classical channel, let us say at lambda 4, and I may convert lambda 3 into a quantum channel, and I send 100 million photons on lambda 4, only one photon should show up on lambda 3. That's what I mean by 80 dB isolation. Or instead of 100 million, I send 1 billion photons on lambda 4, only 10 of them will show up on lambda 3. Right? That is the kind of isolation we need when we try to co-propagate quantum and classical on the same fiber. What is missing so far is I've not yet told you how to add information onto light. And we have to use one of these uh, methods. We can add information, let us say, on the color. We can say if R comes, then it is 1 bit. If violet comes, it is 0 bit. So the color is one way to do it. But that is not as efficient as if I were to use polarization. I can say if it is vertical polarization, the purple arrows, then I will call it a 1 bit. If it is horizontal polarization, then I will call it a 0 bit. So if it's a blue arrows, it's a 0 bit. If it's a vertical arrows, it's 1 bit. Or I can say, hey, wait a minute, I can use phase. If it is 0 phase, then I will call it 0 or pi phase, I'll call it 1 bit. If it's pi by 2 or 3 pi by 2 phase, I'll call it a 0 bit. So there are ways of which we add information, and that is something that we need to understand. Let's take a look at another property that is critical, which is entanglement. And here, for example, we're talking of two particles. Many people ask me, what is the difference between what we do and what somebody else does? The question is, how many photons do you have? If you're talking of only one photon, then you're usually talking of using polarization to transmit information, or phase. If you're talking of two photons, then you could be using what is called entanglement, such that if one orange photon goes to one party, then the blue photon goes to another party. Where is all this being used is the question, right? So let me back up a little bit and say that the primary use for all of this is encrypting data. Okay. We want to keep our data secure. Why do we want to keep our data secure? We want to keep it secure because we are afraid a quantum computer will come and we will not be able to safeguard our private data. So how does cryptography work? There is two parties commonly called Alice and Bob, or transmitter and receiver. They have a public key and a secret key, and there could be a potential eavesdropper. The public key is used to encrypt data from a plain text into ciphertext, and a secret key is used to decrypt data from the ciphertext to the plain text. The whole goal for us is to figure out how to get this key across from transmit to receive without giving any information to the eavesdropper. So classically, what we have been doing is this, which is basically have some random key and we have a function and we multiply that function with some random, we create a function that we send across y of a, and at the other end, the receiver sends back y of b, whatever b is, and both of them have the same key at the end, k. On the transmit side, it's a function a with y of b, and on the receive side, you have k, which is another function b times y of a. Y of b and y of a are the channels, right? You're transmitting a and transmitting b, and you get y of a and y of b on either side. It's a very common protocol. It's called the Diffie-Hellman protocol. But these are secure only assuming there's no quantum computer, right? So what we are trying to do is now make it secure in case there's a quantum computer. And to do that, what we do is quantum key distribution. Okay, so how does quantum key distribution work? Notice on this slide, I have very specifically said free space is 805 nanometers, optical fiber is 1.55 microns. There's a separate quantum channel, a separate classical channel, and then there is, after encryption, there is a standard communication channel. So there are all these channels that are working, and there are many layers to this. There are this layer of authentication, which says, okay, the two parties, the transmit and the receive, are authentic. There is key shifting, which is if the transmit sends 100 photons. Remember, I told you that the probability of receiving it is only 0.01. So transmit will send 100 photons, the receiver will receive 1 photon. Which of those 100 did the receiver receive? That is the process of calling key shifting. The channel may introduce some errors, and so we do what is called error correction. And then finally, in the process of doing key shifting and error correction, we have given away some information to an eavesdropper. So we do what is called privacy amplification. So every QKD protocol will have these 4 steps, all right, of authentication, key shifting, error correction, and privacy amplification. Remember, these are all running on a classical channel. The quantum part of it got over long ago out here when you started sending and receiving photons. Okay. If you want to talk about phase, right, this is also something that we can do classically. So if you look at this is how we would do phase modulation. See, one easy way of doing it is to do binary data sequence. You can send 110000 11010010 and the top curve out here, right? What is called curve 1. You can also do it as a bipolar sequence where you've got the same pattern, but it's shifted so that you get 1 and -1. In optics, we don't use the bipolar because we can either turn on the laser or turn off the laser. So we usually use the binary data sequence. Then there's this notion of a carrier wave. This is that omega that I was talking to you about, right? The frequency omega of the light. Now, in this carrier wave, if I were to change the phase of your ad, introduce these discontinuities, that is called now binary phase shift keying. Why is that? Because I've added a phase every time there's a shift from 1 to 0, I added a phase out here. And then between 0 and 1, I added another phase out here. So this picture of phase being changed is what we can also use to transmit information. These pictures have actually been taken from a tutorial point on digital communication. It has nothing to do with quantum. Many people think that they need to do quantum mechanics all the time, but they don't really need any quantum mechanics. This is just classical communication. And the way we do what is called differential phase shift keying in classical communication is very simple. We have some serial data, we have an XNOR operation, and with 1 bit delay, we send it into this XNOR gate, and then you get out what is called a differential phase shift key. So, for example, you have 0, 0, 1. Out here, there's a transition, you have added this phase. Then from 1 to 1, also you have added a phase. 1 to 0, you have not added a phase. 0 to 1, you have added a phase. So, every time there's a 1 coming after the 0, you're adding a phase, right? 1 to 1, you're adding a phase. But 1 to 0, you don't add the phase. Similarly, 0 to 1, there's a phase. 1 to 0, there's no phase. 0, 0, 0, no phase. But the 1 comes, you add the phase. So you can see from this pattern that this pattern is following a certain logic. And what it is doing is that if I were to do this 1 bit delay and I interfere the gray 1 out here with the white 0 out here, what will happen is I will get an output and I can recover this data. Can we do this with weak coherent states or single photons? The answer is yes. And that is what was demonstrated in 2004 by the Japanese, saying that this is a very nice way of transferring information between two parties who are trying to send secret information. So what are they doing out here? They have a source of light, we call it a coherent pulse source. We have a modulator that is adding this 0 or pi phase shift. Then we have an attenuator, which we are going to reduce the number of photons down till becomes 1 photon. This 1 photon will continue to have this phase. And we transmit it in time bins. You'll see the time bins are out here, separated by some tau. At the receiver, we are going to delay each bit by the same time interval tau. So what happens is there is a longer path and a shorter path. So each bit is now getting interfered with the bit that is coming behind. So if this was time bin 2 and this is time bin 1, then time bin 2 and time bin 1 will interfere. Time bin 3 and 2 will interfere. 4 and 3 will interfere, and so on. What happens if you send just 1 photon? It turns out that if you send one photon, it can be either in the long arm or the short path, but that is not quantum mechanical. In the classical picture, it is either in the short path or in the long path. In the quantum mechanical picture, it is in both paths, and it will interfere. So the leading edge of the photon, which is out here, the long path, will interfere with the trailing edge of a photon in the short path, and then you will detect it in either detector 1 or detector 2, depending on if there's a phase shift or there's no phase shift. This was a very nice idea that the Japanese came up with, and the same thing is explained out here, but slightly different. It says that look, you start with a recurrent source, which is a pulse, you send it in 3 different superposition states. It can be in superposition A, B, or C. And then when it comes here, you are adding the bits 1, 0 or 1, 0 on using what is called a phase modulator and transmitting it through. So if there is a phase difference, then you get a different color. If there is no phase difference, then you won't get a different color, right? And then at the other end, you can recover it by sending it through another one of these delay lines with the same time interval t. One activity that we did was to see if we can bring the red and the blue closer and closer together. And it turns out that you can just make t equal to 0 and carve out a larger pulse of 3t using the same phase modulator into red, blue, and red. And that was one of the works that one of my previous PhD students did. And he showed that the two schemes give you the same results, right? So you can just take the laser, use an intensity modulator to make it into a 3 nanosecond pulse, apply a optical attenuator to bring it down to a single photon, apply the phase modulator, and depending on where the phase modulator, which is this dotted blue line, is sitting, you will get either a 0 or a pi phase shift, or if it's sitting in the middle, you get a pi phase shift because you have 2 times you are adding the phase. Out here, if you're adding the phase once, you'll get a pi and a 0 phase shift. If the phase shifter is out of the optical pulse, and you get a 0, 0, right? So depending on where you locate the phase modulator in blue within the optical pulse, which is in red, you will get a different phase condition. And if you compare the two schemes, you compare the scheme out here, which is scheme A, and the scheme down here, which is scheme B. If you compare the output of these two schemes, you will find that they give you pretty much very similar results. In fact, scheme A gives you more errors than scheme B, where scheme B is very clean. There are no errors in the middle. Scheme A gives you more errors in the middle, right? The total counts are similar, but you do need to spend a little more time post-processing in scheme B, which is not too bad. Even today's computers can post-process very fast, right? So this is an interesting way of sending information on a photon where you manipulate its phase using what is called differential phase shift key, right? So that's one nice example. Now, one of the things that is important is timing, and timing matters, right? When we say that we are receiving a photon, everyone wants to know at what time did we receive the photon. And this is how a single photon detector works. When a photon comes and hits this single photon, actually it hits an avalanche photodiode, there is a current that is generated, and that current that is generated is synchronous with what is called a gate pulse. So this gate pulse and this reference bias voltage are applied together to this avalanche photodiode. If the arrival of the photon and the arrival of the gate pulse coincide, then you end up with a signal at the output of the comparator. And this idea we can then use to determine when the photon arrives. Is the photon arrive at the start of the gate? Does it arrive at the end of the gate? When should the photon arrive, right? And here you will see that we are able to say that the photon arrives with an accuracy of about 250 picoseconds. And that's a good number for us, because remember, we were talking of using 1 nanosecond or 3 nanoseconds. And we want to know if its photon arrives in the first 1 nanosecond or in the second 1 nanosecond or in the third 1 nanosecond. And we can say that with an accuracy of 250 picoseconds. So that's a pretty good experiment by itself, right? So what do these things look like? If you start looking at it, they actually look like network communication boxes. On one side, you have the optics, which is shown in red. You have a laser, you have an isolator, you have an intensity modulator, a phase modulator, an attenuator. On the other side, you have the detectors. In the middle is your fiber spool. This is outside the boxes. You also have these multiplexers and demultiplexers. What are these? Remember those wavelengths that I was telling you about, the Q channel and the C channel? Those can all go out on different wavelengths. They get combined using a multiplexer onto this fiber spool, and then they get demultiplexed and they come out and they go back to the FPGA boards, right? So a lot of electronics, both on the transmit side and on the receive side. And separately, there is a clock that is being transmitted and received. There's a master clock M and a slave clock on the other side. And that is also going on the same optical fiber. So if you look at all of this, it might look complicated, but it's actually very simple. This is a typical example. This is an evaluation board. You can see the word zinc out here. This is an FPGA family from Xilinx. There's a little smaller board out here that we had built to take the signals out from the FPGA. And this is the optics. The optic is quite simple. There is, again, as I said, there is a modulator out here. There's a modulator out here. This will probably be the intensity modulator. This will be the phase modulator. And then you have the multiplexer out here, this little box at the middle of the left, black box that combines the different wavelengths. So it's not very complicated. The signals are fairly simple. As I said, you'll see out here, you have an intensity modulator, a phase modulator. And these two are the main components. And then there is an attenuator. And those will be visible out here. I think the attenuator is sitting down here. You have an intensity modulator here and a phase modulator here. And that's pretty much it, right? So it's a very simple optoelectronic assembly. A lot of the work is in doing those 4 items that I had mentioned earlier. These 4 items, right? You have to do all of this on the FPGA. So there's authentication, key shifting, error correction, and privacy amplification that has to be implemented on the FPGA. And then you control the laser and the detectors from the same FPGA, right? Okay. What is it that we have done so far, right? What we have done so far is we have built networks. We have done simple point-to-point demonstrations, but we have also built networks. Oops, sorry. I clicked the wrong button. Yeah. We have built these networks. So you will see those same boxes that I showed you. They are sitting at 3 different locations. They sit at IIT Madras. They sit at the IIT Madras Research Park. They sit at the Society for Electronic Transaction Security. And they send these photons from one end to the other using the same phase modulation that I described, right? This was one of the first networks in India. It was the point-to-multipoint network, and it had a synchronized clock at picoseconds. Remember, I said 250 picoseconds because I am using 1 nanosecond pulses. I need picosecond clock resolution, and that is also something that we do, right? So, how do you compare quantum key distribution? And I think what this chart, I like it, and you will see the reference down here. It's important to compare it correctly. A lot of people don't fully understand this comparison, and I want to make it a little clear that it is not that we are the first or we will be the last. Everybody is doing these things. You will see Japanese, Switzerland, Chinese, UK in this data, right? But you notice that they all do slightly different things. So somebody might have 6 nodes, somebody might have 5 nodes, somebody has 2 nodes. Some of them are doing it inside a laboratory. Some of us, them like us, are doing it partially in the field, partially in the laboratory. What is important is not the distance. And people say that the distance is important, but it's not the distance. If you look at it, we can claim 90 kilometers, but the loss is 30 decibels. 30 decibels is not 90 kilometers. I did the math for you. 100 kilometers is 20 decibels. 90 kilometer, 30 decibels means that there are losses along this fiber. Similarly, when we did it, 5 kilometers, 3.5 decibels. 3.5 decibels is something like 15 kilometers, but we are getting it that loss only over 5 kilometers. 7.5 decibels is something like 35 kilometers, but we are getting that loss over 5 kilometers. So it's not sufficient to quote only the distance. You have to worry about the loss. The other thing you have to worry about is the rate. So someone is doing in megabits per second, 2580 kilobits per second, whereas everybody else is still stuck at kilobits per second. Right? Someone is running it for 1 day. Someone is running it for 580 days. There's a big difference in the stabilities, right? Some people are running it with 20 decibels dBm of power. 20 dBm of power is 100 milliwatts. Others are running it at 12.9 dBm or 13 dBm. This is 20 milliwatts, 100 milliwatts, 20 milliwatts. So the amount of power that you're launching is also very different. So when you're comparing these things, please be careful. They're not all apples to apples, right? So what are we trying to do? We are actually trying to build these kind of networks, right? If you look at the network itself, the network has a cryptographic application that is working on the cloud. It has a QKD network in the bottom. So this is the physical layer, and you have what are called QKD modules sitting inside a QKD trusted node, and each node is then connected to another node on this fiber, optical fiber. And remember, I told you the International Telecommunication Union, they are putting out standards that tell you how to connect these things together. So each of these secure nodes could be a different vendor. We have multiple vendors in India itself, and each of them could be a different vendor. But they have to talk like this with each other if you have to build this QKD network. You see on the right a very nice picture of how Germany is trying to do it, right? They're doing what are called relay nodes, these little purple dots, green dots, and then you have the access nodes at the end, which are the purple dots, right? So this is how a typical QKD network would start working. What about India? Well, India has that 5 node network that is in Chennai. There are similar networks that are in other places. In Delhi, there is one that has been running, that has been set up by CDOT. So you'll see that you have a user interface that sort of tells you, okay, the greens are working, the reds are not working. Can we set up the keys between different nodes, right? And this is software that has been built by CDAC Trivandrum, and it is used to manage things. So here, for example, is an idea that we have been working on, which is to connect Chennai and Bangalore on this fiber. So this is actual fiber from BSNL, and each of these white circles is one of their stations, and we want to be able to connect it over fiber and demonstrate that we can send a single photon from Chennai and maybe recover it at Sri Perumbadur, send it again to Kanchipuram, recover it and send it to Cheyar, and so on until we get to Bangalore. And when we are able to do that, then the information that we send from Chennai to Bangalore can be encrypted with the key that was generated using these information from the single photons. So I want to be very clear about something. It is, we call it quantum key distribution. It is actually called classical key distributed using the quantum properties of light. Okay, it's very hard to keep saying that, so we call it QKD and quantum key distribution. But the keys or your passwords are still very classical. They are bits, ones and zeros. So there's nothing quantum about that. It is when we are transmitting it using either the polarization or the phase that we are generating it as a quantum bit. All right. Okay. Uh, I think I have another 15 minutes left and I have lots of slides. So I don't go through all of them. What I'll instead do is maybe pause out here and see if people have questions very specific to some of the material, and then I can use my slides to answer those.
There is one single question which is probably you might have covered also, which is why there are losses in the fiber.
Okay. So, yeah, the losses in the fiber are two, two or three reasons. One is, of course, okay, maybe I have some slides, I will show them. That would be interesting also. Okay, let me show this slide. Okay, this is something that I was teaching very recently. It's called an optical time domain reflectometer. And you'll see this picture out here of an OTDR that sends a pulse of light. And every time there's a break, there's a splice in the fiber, there's a little dip. And then there's a connector pair, and then there's a reflection. And you will see another peak out here, and then there's a fiber bend. You'll see another dip out here. Mechanical splice is again another peak out here, and the end of the fiber is another peak. So this is very typical, what is called. The slope of this line, and remember the y-axis here is in decibels, the slope of this line gives you the loss in the fiber, and it is due to this phenomenon called Rayleigh scattering. Microscopic refractive index fluctuation in the fiber, it is inversely proportional to the fourth wavelength, lambda to the power 4, fourth power of the light. The sharp reflections are because you're going from air to glass or glass to air, and that is given by this formula. It is called the, sorry, let me go full screen. It is basically caused by change in refractive index. So you'll see if glass is 1.5 and air is 1, then this becomes 1.5 minus 1, which is 0.5, divided by 1.5 plus 1, which is 2.5. 0.5 by 2.5 is 1/5. You square it, it becomes 1 by 25. So every time there is one of these things, 1 over 25 of the power gets reflected, and you'll see this as a spike. So this is just a textbook picture, but if you look at the fiber between IIT Madras and IIT Madras Research Park, you will see at the hostel there is a huge reflection. There's a connector loss about 3 kilometers away, right? Which we cleaned up, and once we cleaned it, we couldn't see that it is out here. So you'll see the number of connections that we have. We have 1, 2, 3, 4, 4 large connections and maybe a couple of smaller ones, right? So just the quality of the fiber that we are using causes losses from one end to the other end, right? These can also be places where people tap your information and you don't know that, right? So if you look at it, look at this. This is how a splice box should look like. And you can see that the reality is what is at the bottom out here. It is dirty, it is all messy, and light can also leak out, right? So there are some not so simple problems that affect us. And this is a real issue because look at this picture. I have two splices. I'm sending classical on one side and I'm putting my quantum on the other. And the two fibers are very far apart. Remember, I was talking about using one fiber with two colors of light. Here I'm using two fibers, 1 inch apart. I'm sending a clock. This is the clock that I'm sending, 16 nanoseconds on the classical channel. I'm not sending anything on the quantum channel, but my quantum channel has a single photon detector. It can detect photons. See this picture on the right. When the clock is there, I can see it coming out, 16 nanoseconds. When there's no clock, I don't see anything. It's all in the noise. These are real problems with security, right? Anyone could go back and pay the fellow 100 rupees to go and sit out here and put a single photon detector, and you will start collecting the data that is already available to you on the classical channel. So you have to encrypt it. You also have to make sure that it is encrypted with a quantum secure password. So there are both challenges that are there today. And the losses in the fibers are simply this. There's Rayleigh scattering and there's Fresnel refractions. I hope that was reasonably clear.
So that's the only question which was posted during
Okay.
your
I guess it's
previous
been a
session.
long
So
day and so people are also tired. Uh,
pro-
if there are any questions, I'm happy to take them. Um,
no, that's the only question.
okay. There is one more that's come. Will you share the slides to us, sir? I do not know. Are you recording this lecture?
Yes, I'm recording. This is I mean live telecasted on YouTube.
Yeah, so it will be there then. So I think you guys will get the slide, the recording anyway. So you will have the slides. Okay. All right. If there are no other questions, then we could stop here unless
Sure.
people want to listen to more. I mean, I have lots of slides, but okay, maybe what I'll do is let me wrap it up a little differently, right? Let me get you the take home message before we wrap it up. I will tell you what you should remember, right? Before you go for the uh, next talks. Let me just go back to my iPad. All right.
There are two questions which have been posted in last 2 minutes.
Okay.
So
What
one
are
is
the
asking advantages of QKD with SDN.
all right? And what is the other one? How do we minimize losses to ideally zero? Is it possible? I don't think losses are possible. It's not possible to minimize losses. We have to live with them. People are trying to do what is called ultra low loss fibers, and if they succeed, then it will come down. But even ultra low loss fibers will have some loss because physically it's amorphous glass with impurities, and so you do have microstructure that will cause reflections. Right? What are the advantages of? There is no such thing as a quantum fiber. It's all classical fiber. You could lay new fiber, new SMF28 fiber, and that will be better quality than what is already there. What is already there would have absorbed water. It might have many bend losses. Bend losses is very simple to understand. When it bends, you get loss, and over time, these fibers which are inside cables will bend. So that is something that new fiber will not have, right? Uh, what about QKD with SDN? I actually had a slide there that I did not present, and maybe I should present that. Let me do that. Okay, hold on. Let me stop sharing screen out here and instead share it here. Um, Towards the end. Oh no, I don't seem to. Here. Okay. Let's take a look at something like this. This is another picture for a QKD network on how the keys get managed. So this is at the bottom is the quantum layer. In the middle is the key management layer, and the top is a communication layer. And there is this notion of using random number generators and cryptography and so on, post-quantum cryptography, which is actually classical, which sort of lies somewhere between this quantum layer and the key management layer, right? If you think of it from this picture, which is sort of tries to understand better how these networks work. So you could have a completely classical network at the top, right? This classical network, which has encryptor, decryptor, sensitive data, AES, and so on, is entirely classical, and it requires a key. That key is coming from a key orchestrator. That key orchestrator could be using either quantum key distribution or post-quantum cryptography and generating it. If the link, the quantum link in red at the below is actually live, then the key orchestrator will generate a quantum key. I'm saying quantum key, but as I said, it's actually a classical key obtained using the quantum properties of light, or they will generate it using post quantum cryptography, and then they'll transfer it back to the classical network, right? So the classical network also, the quantum key distribution also uses the classical network. So there is a quantum network control and management plane that is also working in the classical network. So where does SDN fit into this? I mean, all of the SDN can control all of this. It can also work a little bit on the key orchestrator. So each of the secure nodes in that other diagram that I had could have a key orchestrator, which is SDN controlled, and then the SDN will then say, okay, I want a key set up between party A and party B, or site A and site B, and then it goes in and does this. So you notice the breakup out where there's a key buffer, there's a secure OS, there's a quantum hardware. So the SDN can control a lot of this stuff that is happening on either side, right? And that is comes into this key orchestrator itself. I hope that's reasonably clear. So how about single photon avalanche diode? What is classical, quantum, and key layer? Okay, so the classical layers are classical um, layer. I mean, whatever we are using Ethernet or something like that, right? That's our classical layer. The quantum layer is where we are using single photons, right? On the physical channel, it's still fiber, but classical is where you have many millions of photons. Quantum is where you have single photons, right? There could be one fiber, they could be the same fiber at different wavelengths, there could be two different fibers. The key layer is a logical layer. It is saying that, okay, I have these passwords. Think of key as passwords. I have these passwords sitting at different places, and how do I manage them? How do I know that password from person A and password from person B are the same, right? So that is managed by this key, and there is this key management layer that does that. Mahesh has to be a little more clear about what he means by how about single photon avalanche diode. I'm not sure what the question there is.
I mean, it was a comment probably when you were discussing this slide. At that time, it was posted. Probably,
The current slide?
yes.
No, I don't think so. This current slide does not really say anything about a single photon diode. The single photon diodes will be sitting inside this red box that says quantum hardware out here, right? It says quantum hardware. That's where the single photon diodes will be sitting there.
We missed one question, which is any difference between legacy fiber link and quantum fiber link from end-to-end power budget link?
Uh, no, I don't think there is any difference in the power budgeting. It's just that the power budgeting is always done from transmit to receive, and the receivers in a classical link are not as sensitive, and the power is very high. In the quantum links, the transmitted power is very low. It is the energy of a single photon, and the receiver has to be that much more sensitive. So there is this factor of 1,000, where the receiver is 1,000 times more sensitive in the case of a quantum fiber link. It's not really a quantum fiber link. In the case of a quantum link, the because the receiver is 1,000 times more sensitive, we can make the transmitted power 1,000 times weaker. Right? That is primarily it. After that, it's a lot of interpretation of how we are transmitting. Most classical communication today in India, at least on fiber, is just on-off keying. 1010 is just on-off keying, right? Like I had shown you. But quantum communications is not using on-off keying. It is using more of phase or polarization.
Okay, so there is one more question linked maybe. So basically, if I understand the question correctly, they are trying to ask how this quantum communication, because when we talk about quantum computing, generally we talk about qubits. So how it is related to qubits, or there is no role of qubit here?
Yeah, so there is no direct role of a qubit as such. I mean, since you could consider one bit when we say we are sending a 1011, we could consider that each of those as a qubits. But unlike in computing, where we are trying to manipulate them and do a computation, we are not really manipulating. We are encoding the one or the zero on a single photon and calling it a qubit, and then we're just transmitting it forward. Right? It is not really supposed to talk to another qubit. So there is a difference out there in the terminology between um, uh, what we do for quantum computing and what we do for quantum communications. Uh, Spin or charge are not really very good for communications, because photons are the best. They fly at speed of light. Electrons will have to go on a copper wire, and they will their information will get destroyed. The spin of the electron is even more easy to destroy, so we don't do any communications with that.
Okay, all right. So that's it. There are. I'm not
Saying
sure what
difference
the
between
question is trying
standard
to ask.
communication channel, classical channel, I don't understand the question,
Yes.
but it's okay. I think people can write to me if they have
Sure.
questions.
Sure. So we can possibly end the session here. So
All
thank
right.
you, Professor Prabhakar, for taking time and answering the queries of the participants raised during the 2-hour sessions. And we hope to see you as an expert speaker in our future FDPs, preferably in offline FDPs if we are able to organize some.
Yes, I think that those are always more fun. Then I can actually show my demos in real life.
Sure, sure. Thank you
All
very
right.
much.
Thank you. Thank you.
So participants,